In the last episode, we discussed the statistics of electrons. Now we will deal with the construction of the many electron wave function and the solution of the Schrödinger equation for many electron atoms. In constructing the wave function for a many electron atom or molecule, the arrangement with electron 1 having alpha spin and electron 2 having beta spin, and that with electron 2 having alpha spin and electron 1 having beta spin are indistinguishable. Since electrons are fermions, we thus need to ensure that the wave function is antisymmetric to the interchange of electrons. Thus, for the helium atom with 2 electrons in the 1s level, we can form an antisymmetric ground state wave function for helium by taking an antisymmetric linear combination of the two arrangements, the one with electron 1 having alpha spin, electron 2 having beta spin, and the arrangement with electron 1 having beta spin and electron 2 having alpha spin. We take the antisymmetric linear combination of these. The 1 upon root 2 factor comes from normalization. This procedure is known as antisymmetrization. For many electron atoms and molecules, we have to consider all such permutations of all pairs of electrons, and each time we interchange the coordinates of a pair of electrons, we have to flip the sign of the wave function. Symbolically, this is represented by the antisymmetrization operator A equals sigma p minus 1 to the power p, where this p is the permutation operator and the index p counts the number of permutations. The antisymmetric 2-electron ground state wave function for helium can be conveniently written in the form of a determinant, which is known as the Slater determinant. If we expand this out, we see that this is just psi equal to 1 upon root 2, 1s alpha 1, 1s beta 2 minus 1s beta 1, 1s alpha 2, which is the wave function we wrote in the previous slide. In the n-electron case, there are factorial n possible pairwise permutations, and that gives rise to a 1 upon factorial n normalization constant. Note that here the alpha and beta spin functions are orthogonal, as they are eigenfunctions of Sz corresponding to different eigenvalues. That is, the alpha spin corresponds to ms equal to plus half, and the beta spin corresponds to ms equal to minus half, and therefore bra alpha beta ket is equal to 0. Writing the Slater determinant for a 3-electron wave function, for example for lithium atom, this becomes the ms equal to plus half wave function is 1 upon square root of factorial 3 times the determinant 1s alpha 1, 1s beta 1, 2s alpha 1, 1s alpha 2, 1s beta 2, 2s alpha 2, 1s alpha 3, 1s beta 3, 2s alpha 3. We see that we can form this determinant by writing the orbitals. Each spin orbital, that is a combination of the orbital and the spin, is written in a separate column, and the different rows vary just in the numbering of the electrons. So the first row has electron 1, second row has the same but with electron 2, third row is the same but with electron 3. Of course, this is just the ms equal to plus half component, that is where the unpaired electron in lithium has up spin. We'll also have the ms equal to minus half component, where the unpaired electron in lithium has down spin or beta spin. Okay, so this ms equal to plus half state will be degenerate with the ms equal to minus half state, and this is known as the Kramer's doublet. So for the ms equal to minus half wave function, we have 1 upon square root of factorial 3, 1s alpha 1, 1s beta 1, 2s beta 1, 1s alpha 2, 1s beta 2, 2s beta 2, 1s alpha 3, 1s beta 3, 2s beta 3. We now turn to some common approximation methods that are used in quantum physics and quantum chemistry. We have seen the quote by Paul Adrien Maurice Dirac in 1929, and you can find this also in his famous book, The Principles of Quantum Mechanics. And the quote is that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. So in other words, the laws of quantum mechanics that we have already discussed are sufficient to explain a large part of physics and the whole of chemistry. Okay? The problem is only that the equations are too complicated to solve manually or to solve exactly. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. There are two classes of approximation methods, two broad classes of approximation methods that are commonly used in quantum physics and quantum chemistry, and these are the variation method and the perturbation method. Now, both of these are derived from classical mechanics. They are not new or peculiar to quantum mechanics. In fact, the variation method comes straight from the calculus of variations. But we will just discuss these, as these are fundamental to much of the methods that are used. The variation theorem states that the energy evaluated from an approximate wave function will always be greater than the lowest eigenvalue of the Hamiltonian. That is, if we calculate the average energy of a Hamiltonian by taking its expectation value with an approximate wave function, the energy we get will always be higher than the true ground state energy of that Hamiltonian. Stated more mathematically, the true ground state energy forms a lower bound to the energy expectation value obtained from any approximate or trial wave function. The proof of the theorem is quite straightforward. Let phi be an approximate wave function. It's not necessary that it's normalized. We need to prove, therefore, that the energy expectation value obtained with this wave function, that is bra phi h phi ket divided by bra phi phi ket, is greater than E0, the true ground state energy of the Hamiltonian H. So let us expand phi in terms of the set of eigenvalues psi I of the Hamiltonian. Since the Hamiltonian is a Hermitian operator, its eigenfunctions form a complete set, and therefore we can expand phi in terms of the eigenfunctions psi I of the Hamiltonian H. Therefore, phi equals sigma I Ci psi I. So now the norm bra phi phi ket is equal to bra sigma I Ci psi I sigma j Cj psi j ket, which is equal to, taking Ci and Cj outside the bracket, since they are just numbers, is equal to sigma I sigma j Ci star Cj bra psi I psi j ket. Remember that in the bra, the Ci has to be complex conjugated. But now, since psi I and psi j form an orthonormal basis, this is equal to sigma I, sigma j, ci star, cj, delta ij, where delta ij is the Kronecker delta, which is equal to 1 for I equal to j and equal to 0 for I not equal to j. Due to the orthonormality of psi I, the only terms that survive are where I equal to j. That is, bra phi ket is equal to sigma I ci modulus squared. Since since delta ij equal to 1 only when I equal to j and equal to 0 for every other case, this double summation reduces to the single summation sigma I ci star ci or sigma I modulus of ci squared. Okay. Similarly, bra phi h phi ket is equal to sigma I sigma j ci star cj bra psi I h psi j, but that is equal to sigma I sigma j ci star cj bra psi I ej psi j ket, since psi j is an eigenfunction of h, and since psi I and psi j are orthogonal unless I equal to j, this becomes sigma I sigma j ci star cj ej delta ij, and then expanding this double summation gives us the single summation sigma I ci modulus of ci squared ei, since delta ij is equal to 1 only when I equal to j and is equal to 0 otherwise. Remember, we need to prove that bra phi h phi ket divided by bra phi ket is greater than E0, but the numerator is sigma I modulus of ci squared ei and the denominator is sigma I ci squared. Therefore, in other words, we need to show that sigma I modulus of ci squared ei divided by sigma I modulus of ci squared is greater than E0, or in other words, that sigma I ci modulus of ci squared ei is greater than E0 times sigma I modulus of ci squared, or in other words, sigma I modulus of ci squared times ei minus E0 is greater than 0. But this has to be true, since the modulus of ci squared has to be positive, and E0 is the ground state energy. Therefore, ei minus E0 also has to be positive. Ei is greater than E0 for all I greater than or equal to 0. So this statement is trivially true, or in other words, therefore we have proved the variation theorem. The variation procedure provides a way to approach the true wave function through systematic approximations. We start with a trial wave function phi and expand that trial wave function in terms of a basis set psi I. Thus, phi equals sigma I ci psi I. Next, we compute the energy expectation value for this wave function, that is bra phi h phi ket divided by bra phi phi ket, and then minimize this energy expectation value with respect to the coefficients ci, that is, keep varying the coefficients until the energy does not decrease any further. This then is the best energy that we can obtain with that basis set. Expanding the trial wave function phi in terms of a basis set psi I consisting of n functions, that is phi equals sigma I ci psi I, the energy E is equal to sigma I sigma j Ci star Cj Hij divided by Ci star Cj Sij, where Hij is the matrix element of the Hamiltonian, that is bra psi I H psi j ket, and Sij is the matrix element of the overlap matrix between psi I and psi j. Thus, sigma I sigma j Ci star Cj times Hij minus Esij equal to 0. Differentiating this with respect to the coefficients, we see that Hij and Sij being given by these expressions, they don't depend upon the coefficients. They only depend upon the chosen basis. Therefore, we get twice sigma I Ci into Hik minus Esik minus sigma I sigma j Ci star Cj Sij times del E by del Ck equal to 0. For the variation theorem to be satisfied, that is for the energy to be a minimum, we require that del E by del Ck is equal to 0 for all k. That is, in this equation the second term goes to 0, and therefore we are left with sigma I Ci Hik minus Esik equal to 0. There is one such equation for each coefficient Ck that can be varied, and this gives a set of n linear equations in the n unknowns Ck. And for these linear equations to have a non-trivial solution, the secular determinant has to be 0. That is, the determinant of Hik minus Esik is equal to 0. This is known as the secular equation. Thus, we have a system of n simultaneous linear equations in n unknowns of this form, and that can be written in matrix form by this matrix times the coefficient matrix is equal to 0. For this set of equations to have a non-trivial solution, the secular determinant has to be 0. That means that this equation can be satisfied either if all the coefficients are 0, which is just a trivial solution. All the coefficients are 0 means the wave function is 0, which means the probability is 0. That's a trivial solution. Or the determinant, this secular determinant, has to be equal to 0. If the original basis set was chosen to be orthonormal, that is Sij equals delta Ij, the secular determinant reduces to this simpler form. Let us solve this for the case n equal to 2. So then we have h11 minus e, h12, h21, h22 minus e, determinant is equal to 0, or h11 minus e into h22 minus e minus h12 squared equal to 0, or e squared minus h11 plus h22e plus h11 h22 minus h12 squared equal to 0, or e is equal to half h11 plus h22 plus or minus half square root of h11 minus h22 squared plus 4h12 squared. The second approximation method we will discuss today is the perturbation procedure, which is useful when we know the eigenstates of some zero order Hamiltonian H0. That is, we know the eigenstates psi I0 of the Hamiltonian H0. The H0 psi I0 equals EI0 psi I0. And we wish to find the eigenstates of some other Hamiltonian H which is not too different from H0. That is, we can write H is equal to H0 plus some perturbation H dash, where the perturbation H dash is much smaller than H0. Further, let the eigenfunctions and eigenvalues of the full Hamiltonian be given by H psi I equals EI psi I. We want to find the EI and the psi I. Expand the wave function psi I in terms of the zero order wave function psi j0. since the zero order Hamiltonian H0 is a Hermitian operator, its eigenfunction psi 0 form a complete set, and therefore we can perform this expansion. So we write psi I equals psi I 0 plus sigma j not equal to I Cij psi j 0, or thus H minus Ei operating on psi I 0 plus sigma j not equal to I Cij H minus Ei operating on psi j 0 equal to 0. But since H is equal to H0 plus H dash, we can put that in here and write H dash plus Ei0 minus Ei operating on psi I0, since the H0 operating on psi I0 will give you Ei0 times psi I0. Then the second term is plus sigma j not equal to I Cij H dash plus Ej0 minus Ei operating on psi j 0. Again, H0 operating on psi j 0 gives you Ej0 psi j 0. Okay. Left multiplying this equation by bra psi I 0 and using the orthonormality condition, this reduces to Hii dash plus Ei0 minus Ei plus sigma j not equal to I Cij Hij dash equal to 0, where the Hij dash are the matrix elements of the perturbation Hamiltonian H dash between the zero order bra and ket. Likewise, left multiplying by psi k0, where k is not equal to I, we get hki dash plus cik times hkk dash plus ek0 minus ei plus sigma j not equal to I or k cij hkj dash equal to 0. Now we expand the energy and the coefficients as Ei equals Ei0 plus the first order correction Ei dash plus the second order correction Ei double dash plus etc. And similarly Cij is equal to Cij dash plus Cij double dash plus etc. Performing these expansions and neglecting all second order and higher order terms in this equation, we see that the second term goes to 0, since substituting Cij in here, all terms have 2 or more primes, that is that are of second order or higher order, and substituting the first order approximation Ei equal to Ei0 plus Ei dash for Ei in here, Ei0 cancels and we get Hii dash minus Ei dash is equal to 0, or Ei dash is equal to Hii dash, which is equal to bra psi I0 H dash psi I0 ket, or in other words, the first order correction to the energy Ei dash is the expectation value of the perturbing Hamiltonian H dash in the zero order basis psi I0. Likewise, from the expression hki dash plus cik dash into ek0 minus ei equal to 0, taking the first order approximation in here, since cik dash is already of first order, if we retain only the zero order term for ei, that is ei equal to ei0, we get cik dash is equal to hki dash divided by Ei0 minus Ek0. Okay. To get the second order corrections, we use the first order expressions and neglect all terms beyond second order to give minus Ei double dash plus sigma j not equal to I Cij dash Hij dash is equal to 0. But we have shown that Cij dash is equal to Hij dash by Ei0 minus Ej0. So putting that expression for Cij dash in here gives the second order correction to the energy as Ei double dash is equal to sigma j not equal to I Hji dash times Hij dash divided by Ei0 minus Ej0. Because of the energy difference denominator in this expression, the states which have the largest effect on psi I0 are those which are closest in energy to it. Also, because of the energy difference denominator, the criterion for the validity of the perturbation expansion is HKI dash has to be very much less than the energy difference. This form of the perturbation theory breaks down for degenerate states. For degenerate states, we then have to go for degenerate perturbation theory.